All right, we have a test on Wednesday. I don't know what day that is, maybe the 2nd. And the relevant assignments for that and lectures for that is everything up through the 24th on Wednesday, 2 days ago. Remember that all these exams are cumulative, so you need to go back and remind yourself about anything that that we've done that you haven't thought about for a while. And the topics are through rigid body kinetics. So the new thing that we're going to start today is linkages, and that's not going to be on the test. Before I get started with new stuff, does anyone have any questions on homework problems or anything? Yep.
I think I did email you about that. I have some questions regarding. Okay, February 22nd.
Mm-hmm.
Number 3.
Okay, so for number 3, this is Monday, 2/22, number 3. You have a rigid body that makes an angle of 50 degrees with the horizontal. It has a length of 2. And a mass of 50 kilograms. At the instant shown, the angular velocity is negative 10 radians per second. And down is towards the bottom of the page, so we have to put a weight in that direction. So first, what's the angular acceleration? We know some stuff about forces. We're trying to figure out stuff about motion, so we know we have to go to Newton's second law. That means we need a free body diagram. So what forces act? Weight. And so that's 490.5. And now go around the boundary looking for contact. So where's there's contact with the outside world? The pin. A pin joint applies a unknown force vector. So call that R. And let's put the coordinate system at the pin. Oh, I didn't go through the steps. The steps. Let's do the steps. That's step 3. Let's do it Memento style. Remember that movie? Yeah. So now, I look at my tattoo and I'm like, oh, step 2 is this. When you see that movie, you're going to think back and be like, wow, that thing I didn't laugh at was super funny in class. Okay, so step 1. Is there a fixed point or not? Yes. So the about point has to be at the pin. And so the moment of inertia about the pin is equal to the moment of inertia about the center of mass, 1/12 times 50 times 2 squared, plus the parallel axis theorem. So that's the moment of inertia about the center of mass. The parallel axis theorem part is the mass times the distance from the center of mass to the point that we care about. So what's that length, that distance? This is 2 meters long, so 1. And can someone tell me what that is? 200. Okay, kilogram meters squared. Okay, and then step 3 is the free body diagram. So now, pancake table, pancake, artist, row, 4, marzipan. I expect to hear you say that out loud during the test every time you do it. No, please don't do that, really. Okay, so the force R is acting at where I put the origin. The about point has to be at the origin. That's where the fixed point is. So subtract and you get a row vector of 0. The force vector is Rx, Ry. And there's no moment. And then the weight is acting at, I think, 0.643, 0.766. That's the midpoint. Same about point. So the row vector is 0.643, 0.766. The force vector is 0, negative 490.5. And what do you get? 0.643 times 490.5. Okay. Yeah. You could, sure, but then you have to then you also have to use sine and cosine to represent the weight, so I'm not sure it would save you any time. You know what I mean? But yeah, that would be perfectly fine. Okay, step 5. That's Newton's second law. Do we want to use it here? No. So no step 5. Step 6 is the rotational equation, and that says negative 315.39 is equal to 66.67 times alpha. So what's alpha?
Negative 4.73.
Okay, and that's radians per second squared. If you want to write it as a vector, that's happening in the z direction, so that's 0, 0, negative 4.73 radians per second squared. All right, that's the angular acceleration. Now for part B, how do we get the acceleration of the center of mass? Yeah, that's right. There should, ideally, anything about the center of mass, well, when you're doing a problem like this, I think that question, what's the acceleration of the center of mass, should trigger two things in your mind, two possible ways to go. One is we already know the angular acceleration, so the watermelon equation seems like a reasonable way to go, and that's the one we're going to end up using. The other one is that we didn't use it on our first pass, but Newton's second law relates to the center of mass. So that should also trigger a question like, would Newton's second law make this an easy calculation? It turns out in this case it wouldn't, because we don't know that force yet. But, and we're going to use Newton's second law for the question you're asking about. But yeah, that any acceleration of the center of mass, anytime that comes up in a problem, that should trigger, like, Newton's second law talks about that. Like, that's a possible route. Okay. Well, we're going to use that the acceleration of the center of mass is equal to alpha cross r plus omega cross quantity, omega cross r, watermelon equation. Alpha, we just got 0, 0, negative 4.73. The circular motion we're talking about here, if this is the center of mass, is the circular path of that point around the pin. What? Yeah. Well, there's also...
I mean, like, are you trying to ask what's the radius?
I'm just trying to show, I'm just showing on here what the circular motion, that watermelon equation refers to circular and spherical motion. Okay, so what's the circular or spherical motion we're talking about? We're talking about the circular path of the center of mass around that pin. Okay, and R goes from the center of the circular motion or spherical motion to the point that you care about. So that blue vector is the R. So R is positive 0.643, positive 0.766, 0. Then omega is given. That's 0, 0, negative 10. And we're crossing that with 0, 0, negative 10 cross R. So 0.643, 0.766, 0. Anybody have a quick way to plug that into their calculator?
I got negative 60.68 and negative 79.64.
Okay. Does it make sense that we have a 0 component in Z? Yeah, because all this is happening in the xy plane, so all the translational quantities have to be in the xy plane. Only the rotational ones, well, all the rotational ones just have to be in the Z direction. All right, so that's the acceleration of the center of mass. And B really in this problem is meant to lead you towards an approach for C. Now that we've calculated the acceleration as the center of mass, C asks what's the force vector applied to the rod by the pin. And so this is where we're going to go back and use Newton's second law. Newton's second law says add up all the force vectors. That's equal to the acceleration of the center of mass. And that's what we just calculated. So we can calculate some things about the forces. So if you go back to the free body diagram, Newton's second law says Rx, Ry plus 0, negative 490.5 is equal to the mass times the acceleration we just calculated. And so what do you get for R?
We got negative 3,034 and negative 3491.5.
Okay. Anyone get something different?
For the y component, I got 4,275.
Positive?
Did you subtract? Did you add? Oh,
This one's negative, and this one you would add.
check the acceleration of the rod at the pin is 0. So that's what I did. Do you always have to consider the center of mass of the rod?
For Newton's second law. Newton's second law only tells you about the acceleration for the center of mass.
I was halfway there. Like, I did it, but then the only thing I didn't add was the negative 490.
Oh,
So I wasn't sure.
Yeah.
Like the numbers.
yeah. Well, figuring out that flow is really like the big thing in this problem. But yeah, don't forget to break up all the individual forces.
Thank you.
Sure. Yeah, so I'm glad that came up because that's super important. Newton's second law only talks about the acceleration vector of the center of mass. Any other questions? All right. Well, let's talk about linkages. And linkages are the basis for every kind of it's the basis of machines, robotics. Linkages, it's awesome. Awesomeness. It's the basis of awesomeness. So here's the deal with linkages, and let me give you an example. This is sort of a simple example, and this is the one that I'm going to do. We probably won't get through it today, but the definition of it is a collection of rigid bodies connected by joints that's not in static equilibrium. One more thing. Basis of machines, robots. biomechanics. That's why I like it, because that's the area that I worked in for a long time. And so, like, an example would be, say that you have two members connected there by a pin, and here that pin slides in a slot. And these angles are the same. This is 3 meters long. And let's say you apply 600 newtons to that pin. Thanks. What's the acceleration of the pin in the slot? You can see the similarity with structures that you do in statics, but in structures, for this to be in static equilibrium, rather than a pin in a slot here, this would have to be like another pin joint. That would work. And then you could apply this force. It wouldn't go anywhere, and you could calculate the reactions. But we've removed, or we've added 1 degree of freedom, let it move in 1 dimension, and now this thing's going to accelerate. Wait. Where did I put that? Okay, well, let me give you a set of steps for these problems, and then we'll start doing an example. So the first step is member by member. So for each member, do the rigid body analysis that we've just finished talking about. If the member in one case has a fixed point, then the rotational version of Newton's second law gives one equation in a 2D problem. If you have a 3D problem, that's 3 equations. And if it has no fixed point, then you're going to do Newton's second law and the rotational equation. And that gives you 3 equations in 2D, 6 equations in 3D. In statics problems, then you'd be done. You use Newton's laws for each member, and then you just solve this system of equations. In linkages, you're not done yet. So after you're done with all members, you still have more variables than you have equations. You can't solve the system. So those additional equations that you need are going to come from geometric constraints.
Just a quick question.
Yeah.
For part A, when you say it has a fixed point, you're taking the second smallest, which is one equation in 2D and 3D.
Yep.
Does it mean, like, can it be the case that it would actually give 2 equations in 2D? Or is it always one?
It's always one. It's always just the z component. If you're in the xy plane, it's always parallel to the axis that your motion isn't happening in. So the additional equations that you need come from geometric constraints. And so step 2 at each joint that's not fixed, the geometric constraint equation comes from the requirement that any members connected at a joint, okay, so any joint is joining 2 members, member 1 and member 3 or whatever, and based on the watermelon equation and relative motion, those 2 members have to agree on the acceleration of that joint. That's what the joint does. It restricts accelerations, motions of that contact point. So they must agree. So we're going to use relative motion and watermelon equation to express the acceleration of a joint in terms of each member and then set those equal. this will be, was that clear? No, sorry. It'll be more clear when I do an example. What? Yes. So what you're saying, so basically what you're saying is this. So if you have a joint A let's say it's a pin joint that connects these two members, okay? You can calculate the acceleration of A according to this member. So say this is member 1 and this is member 2. You can write the acceleration of A according to 1 as like the acceleration of the center of mass of 1 plus alpha of 1 cross R1 plus omega 1 cross quantity omega 1 cross R1. This is relative motion. So you follow what I'm doing there? And you can also represent the acceleration of the point A according to body 2. That's equal to the acceleration of the center of mass of 2 plus alpha 2 cross R2 plus omega 2 cross omega 2 cross R2. And the nature of that joint is that the acceleration of A according to 1 has to equal the acceleration of A according to 2. Okay, any questions about that? Well, let's just do the quiz, and I'll do this example on Monday. If on Monday, if you have any questions on homework or whatever, bring them, and I'll answer questions for the exam that's on Wednesday.